Perfect. Thank you, Florence. So you can start anytime you want.
So perhaps I can start. uh, Try to share my screen. So you're supposed to see my screen. It's okay.
Yes, yes, it's working.
So I'm not sure I can see if there are any message. So I don't hesitate to ask some question. Uh, yeah, not sure it's the good slide. Not sure it's the good slide. Okay, perfect. So hello everybody. I'm Arnaud Renard. I'm HPC expert and director of Romeo HPC Center in France. I'm managing HPC projects in 15 years, infrastructure project, scientific project, and collaborative projects with companies. I'm also teaching HPC technologies, parallel and accelerated computing to master students. Perhaps I can add webcam, sorry. So parallel and accelerated computing to master students at University of Reims. I'm also involved in the French Federation of Regional Centers, which is called Maisonette, and in the French Competence Center project EuroHPC. All those activities are related to HPC, and that's the first question. What is HPC? Okay, so let me just set the scene here and present the pillar of science. So traditionally, we've had theory, a paper and pencil sort of way of understanding that what goes around us. If you got some rectangular triangles, you can use Pythagoras theorems. If you've got parallel lines, you can use Thales theorems. If you've got fluids, liquid or gas in pipes or in a tank, like the one you can see on the upper right video, to crystallize beet molasses and transform it into sugar. So with fluids, you can use Navier-Stokes equations. With problems related to electromagnetism, you've got Maxwell equations. And with quantum mechanical systems, there are some Schrödinger equations. And there is a lot of equations in the literature. All of them are theory. It's proven, it's validated, it's in the book, it's implemented in the software, and we can use it. That was augmented by experiments. So the experiments are there to verify, in some sense, the theory that goes on. And we build an experiment, we carry out the ID, we verify the theory, we adjust the theory, we adjust the experiment, and that's the way science is driven forward today. But sometimes it's too difficult to build an experiment. Sometimes it's too expensive. If you want to crash test dozens of vehicles on dozens of trees, it's going to cost a lot of money. If you want to test dozens of different car colors in different environments, varying the design of the car and so on, it will be extremely expensive too. Sometimes it's just too dangerous. And sometimes you can't wait. And sometimes it's not possible. For example, consider the fusion of two neutron stars, the bottom left video. That's an experiment that I really can't perform in a laboratory. The only way really to do it is through simulation. The same thing is true with climate and everything that happens in the future, for example. So we use, not the good, so we use computers to help us understand the science, to augment the theory, and to augment the experimentation by doing numerical simulation. Simulation enables us to understand the observation in the light of the theory, to verify new theory, to create new in-silicon experiments. And those three paradigms can interact in a chain. So there is a chain relationship with the three pillars. We rely on theory to build a digital model, to validate experimental result, and thus to validate new theory. In this numerical simulation, okay. So you've got object, matter, and energy. They are replaced by information, which is the description of this object. The action of the law of the nature is replaced by the algorithm equivalently programmed on the computer. And we shall notice that with this numerical simulation approach, the relationship between physical time and computational time is modified. For example, we can have fast simulation of slow phenomena like climate, for example. We can have slow simulation of fast phenomena like molecular docking, for example, or sometimes we can also have some real-time simulation for automotive rendering, for example, that you can see on the lower right on the slide. So in any case, if we want to model ever larger object and ever more precise microscopic phenomena with the utmost precision, we need very performant computer, the most powerful computer in the world. And the intersection of one, the ability to represent and to manipulate huge objects or systems with the greatest precision, the ability to implement the law of nature with algorithm offering the most accurate and the true results, and running performantly on these supercomputers while taking into account the characteristic of these computers in terms of communication time, data transfer, reading data, writing output, and so on. So all the three challenges altogether is what we call high performance computing, or HPC. So there are two parts. In HPC, there's the hardware, electronics, servers, and so on. There's the software, so software adapted to the machine. About the hardware, we need more powerful computers to calculate faster, with more compute unit, with more memory, with more storage. About the software, we need experts who can take a problem, create a program to solve it, while making the most of all that computing power which is available. Anyway, you can run HPC workload either on a single server in the cloud or in a cluster available at your company or at your research lab. But there is a class of machine that make it possible to run HPC at scale. They are designed to achieve the highest possible performance, particularly in terms of computing speed, and they're called supercomputers. And in this context, we speak of supercomputing. And there is an official list of those supercomputers. It's called Top 500 list. So, no, I've got to. Okay, no, this one. So before talking about the most powerful and innovative supercomputers in the world, the introduction is done. Let me give you a brief introduction of supercomputers, what they are used for, and how we can use them and exploit their performance. So the first supercomputers were created during the World War II to solve military problems, complex physics problems, and encryption problems. So on the left, you got John von Neumann. It's a mathematician. He's the architect of modern supercomputers, of modern computers. Just close to him, you can see Oppenheimer. He's a scientist who led the Manhattan Project, the bomb. And just after, there is Alan Turing. He's a British mathematician, computer scientist, pioneer of artificial intelligence, and he was in the team who cracked Enigma. And I encourage you to watch the two exciting films if you don't know them. So today we are using HPC for engineering to test design with simulation. I give a lot of examples for particle physics to understand the universe, for finance, for risk analysis, market modeling, in astronomy, a lot of usage in petrol engineering, optimizing the oil extraction, in biology to drug design and molecular docking, in computational chemistry, in social science, thanks to big data, mega data analysis, lots of usage in medical analysis images to improve the diagnostic, also for the climate and the weather. We are using it also for precision agriculture to optimize the plants growing, for security with mega data in cybersecurity, and a lot of usage entertainment. I don't know if you can hear the entertainment, animation, film, and video games. We are also using HPC for fluid dynamics to make some simulation to analyze the flow of the system, and in space exploration to simulate the mission and to analyze the data. That's a lot of different topics, and there are more and more topics available. But the question is, what is the architecture of supercomputer? What are they? How can I build a supercomputer? So generally speaking, a supercomputer is made of chips, a lot of chips. The chips like this, made up of cores, which are the elementary computing units. Today, we've got two main types of cores. We've got the CPU, who provide tens to hundreds of cores on the left, and we've got GPU, we can provide 1,000 to 20 or 30,000 cores on the right. And a conventional program will run on the CPU and will send the massive calculation to the GPU, which acts as an extension, as an accelerator, we call it. So the CPU and the GPU will either share or transmit data to each other. They are the building blocks of our supercomputers. On each chip, we have memory, which is shared between cores and which can be accessed very quickly. But one CPU or one GPU is not enough. And because it's not enough, we're going to put several of them on what we call a motherboard to create a compute node, a node, with more CPU and more GPU. Of course, the chip are sharing some memory on the motherboard. So it consists of global address space to read and write data. So our program, our software, will therefore run on the node CPUs, who shared all the CPUs, who shared the same memory and sometimes delegate massive processing to the GPU. It's a shared memory model with shared memory architecture, so that's the hardware part, and a shared memory calculation code will be useful to access this hardware. But one node is not enough. So we are going to put several nodes together. We will even stack them 2 meters high in what we call the cabinet. And so if we want to perform a calculation on the whole cabinet, this time we will talk about distributed model. All those nodes together are considered as one machine with memory distributed on the different nodes, and our software must exploit this distributed memory. It's not easy. Of course, if we want to use it as a single machine, we need a high-performance interconnection network for nodes to exchange data during the computation. This network should be optimized for exchanging data during the calculation. It should be very fast, 400 gigabytes throughput, for example, for sending large amount of data. And it has also to be to provide a very low latency, so that is the delay to transmit the data. So we've got one cabinet, but it's not enough. So since we want to make even bigger calculation, we're going to use a lot of those cabinets and a lot of longer cables, and we will fill complete holes with this cabinet, sometimes spanning several floors. And that's enough. That's enough. We made a supercomputer. And that's how it's working today for the most powerful supercomputer in the world. They are assembled with basic bricks, which are mass-produced components. It's mandatory for an industrial approach. We talk about CPU and GPU, network cards, memory, and everything you need to connect supercomputing between each other. Today, the most powerful machine in the world is hosted by Oak Ridge National Laboratory from the Department of Energy in the US. It's almost 9,000 nodes, close to 9 million core. And in each node, you can see we've got one CPU and 4 GPUs. So we've got 37,000 GPU. They represent 98% of the power of the machine, those GPU. All of them are in 74 cabinets. It consumes 23 megawatts, and it can provide, be careful, 1 billion of computation each second. This counting of the number of computation per second is the way we are expressing the power of a supercomputer. Another one, the most amazing machine in France and in Europe is hosted at my university, University of Rennes, and is operated by my team, the Romeo HPC Center. Some colleagues are here today. It's 58 nodes. On each node, you can see there are 4 couple of closely connected CPU plus GPU specific architecture. We've got 232 CPUs and GPUs. It takes 2 cabinets. The GPUs are representing 95% of the power of this machine. It consumes 160 kilowatts, and it's 100 less than the previous one, so it's 10 million of billions of computation each second. So that's the machine accessible for researcher at the University of Rennes. Okay, it's cool. We got a supercomputer. It can do a lot of things, but the question is, how can I use this supercomputer and how can I exploit this power? So there's a few points to keep in mind. We've got a lot of cores, thousands of cores, and we have to exploit this parallelism. We've got CPU, GPUs, the memory is distributed. We've got a lot of cores. You can put on it a lot of thread. So you have to manage this parallelism. It's not easy. We are providing some courses about on how to use this parallelism, OpenMP, MPI, CUDA, and so on. We've got a lot of them. I will present this just after. We have to manage with the network. So when you've got thousands of nodes, some are very close, sometimes it's very far. So we have to manage this very huge network. There is a point about calculation accuracy. Perhaps you may know that the representation of floating point numbers in your computer, and it's not represented like you can see in your mind. And perhaps modern CPUs or modern GPU are more adapted to AI with low precision number than historical large precision number you can use in science. Perhaps I will not go further on this topic. You also have to manage your data. Sometimes your data are in the CPU memory. Sometimes they are on the memory of the node. Sometimes they are on the hard drive of the node or in the command hard drive attached to the supercomputer. So we will have to manage also this issue of the data. And how to use a supercomputer? The first step is to request some resource to a supercomputer. So generally there's a portal. You can provide a scientific description of your project and you will be granted some resources. The supercomputer can look like that. So on the left, you've got the logging node. Just on the right, the compute node, the place where is the compute power. On the bottom left, management server. As a user, you don't mind that about. And you also get parallel storage server. And all of them are interconnected with high-speed network. So you are on the left on your laptop, and you have to connect to the supercomputer. So to connect, we'll use some SSH protocol to directly connect to the login nodes. You cannot connect to the compute node. So you will connect to the login nodes with SSH. Next step, you have to run a calculation. You will need a batch scheduler to make it possible to wait in the like you can do at the supermarket. So you're at home, you connect in SSH, and just after you describe which kind of resource you want. You describe what you want the resource to compute, and at what time, with Learn, with some commands, very easy commands, your job will be launched on one of the compute nodes. And next step, you have to load the software you need. So a lot of different software management. At Reims, we are using SPAC. Some others are using modules. You also can run some containers if you are familiar with container. And that's the way it works. SSH, SQ, SBatch, Slurm. And next, you will be able to load the software you need with those command tools. And at that moment, your software is running on the compute node. It's not so complicated, but it needs to be done because it's the way all the supercomputers in the world are working. So we're also providing some trainings at the University of Reims. We are providing trainings about how to use SSH and to connect to supercomputer, how to start some jobs on the supercomputers, and how to use the software stack provided by the system. So last part, we're talking about how exploiting the parallelism. There is a summer school which is organized by the Competence Center in France and which is free and which is in English. So I invite you if you want to participate. It's from 23 of June to 7 of July. There is 1 week dedicated to CPUs. You can learn technical to compile, to optimize, to profile your codes on CPUs. The second week is dedicated to GPU. Lots of different technology also to use a GPU in Fortran, in Python, in C, C++ with different approach. All those courses will be online and are free. So you just have to register and you will be able to use these computers. In the context of EDIRE, if you are a partner of the EDIRE project, you can also access to Romeo supercomputer if you want to use our supercomputer for the courses. And there is a lot of other courses provided in France, in Europe. So I give you some different website. You can find information about the courses. And that's it, if you got some question.
Thank you very much, Arno. It was really interesting. Actually, I didn't know much about HPC, so now I'm up to date. Is there any question on the room or even in the class from the student? Everything was clear? Okay, let's move on. Perfect.
Thank you.
Thank you, Arno. Next, I think is Theo.
Yes.
Maybe.
It
Oh,
could
okay.
be me. I'm here. Okay. Okay, all good. Let me just share my screen real quick. It's this one. All right. Okay. 1 sec. Okay, I'm good. I'm good to go. So yeah, so hello everyone. My name is Theo Barrios. I am an AI research engineer who works with Arno at the Romeo HPC Center in Reims. And today I'm going to make a quick introduction on project management when you want to develop artificial intelligence methods. So we hear a lot about artificial intelligence. I think that much is an understatement. But let's review just a few of the applications that can be found. When we think of artificial intelligence, the first thing we think of usually is ChatGPT, at least nowadays. It's like something we can just interact with text and talk to. That's the more recent definition of artificial intelligence. But if we go back a bit, the main moment we would hear about artificial intelligence would be something like video games, which are very different kind of artificial intelligence. But talking about artificial intelligence in one way or another is not an abuse of language. Moving on other application that can be found. we have here, so this is not actually President Emmanuel Macron on this image. This is what we call a deep fake. So the face has been, the face of someone has been changed. And this is just a creative display. And creative industries can also use a lot of artificial intelligence. Here, so for the people not French here, this is a tax form, a French tax form, because that is also a good application of automation of reading on document and automation of digitalization of document. That's an application of artificial intelligence, character recognition, that has been used for quite some time now. It's not just a recent trend. Finally, one we also hear a lot about, and that has yet to come, is the autonomous driving, like a safe autonomous driving, is something that hopefully artificial intelligence will be able to unlock pretty soon. So there is a growth on the interest of artificial intelligence. Let's take as an example the number of GitHub AI projects. So GitHub is basically the biggest repository of open source code. It's a bit more than that, but to summarize, I'm going to keep it that way. For example, you can find the source code of a lot of software that you use that are open. For example, if you know the Linux operating system, you can find all of the code that is on Linux on GitHub, and a lot of different projects. If you use Mozilla Firefox, like the web browser, it can also be found, but the entire code can be found on GitHub. So GitHub, just as a parenthesis, is a good marker on the interest of Project of AI, because it's a big increase of interest over the last year. So that's taken from last year AI index report, because the current, like the 2024 AI index report has just been released today. I can put a link if you're interested at the end of this presentation. So the goal here of this presentation will be first define what is artificial intelligence, what it can do concretely. What it cannot do is also something that needs to be taken into account if you want to apply it to any industrial project. And then we're going to go through the basis on how to use it in the project and what's the reflex you need to have. So the first thing, artificial intelligence, if you want a short definition that is still debatable, like most big definitions, would be the imitation of human problem-solving abilities by a computer program. So the idea is that you have an input and a program that can make a decision, like get maybe some intuition or mimic human intuition, could be called an artificial intelligence. Not every artificial intelligence is data reliant. For example, we have some examples.
Excuse me, Theo.
Yeah.
We have some Zoom issue. So
Okay.
we're gonna have to connect again on using the same link in less than 20 seconds.
All right.
Because the link is gonna. Okay. Thank you for conversion. Thank you, everyone. And that's of course for everyone.
Okay.
We're gonna lose the signal. Okay. Thank you. See you in 30 seconds.
Okay.